All right, how we doing, mathematicians? Okay, so in this video, we are finishing up lesson 1.2. Okay, so this is lesson 1.2. We started it. We got to about here. This is page 13. So what we're going to do is we're going to start off our day today by answering question number 4. And question number 4 is going to kind of help us refresh our memories as to what were we talking about, what's going on. So this is kind of like our previously in math class kind of recap. Okay, so we're given this table here, and the question says, how can you predict that the graph will be a straight line from the patterns in the table? Okay. And then we need to answer what about in the equation, and then of course we're going to explain. Okay, so I want you guys to take a minute, talk to each other. How do you know exactly that this table here in question number 4 is going to create a straight line? How do you know from the table, and then how do you know from these equations that we wrote last class? Okay, so take a minute, pause the video now, discuss, and then we'll talk about it afterwards. Okay, so hopefully you pause the video and discuss this. So how can you predict that the graph will be a straight line from the patterns in the table? So remember, to determine from a table if we have a linear relationship, you're going to be looking at both the independent variables and the dependent variables. How are they changing? So remember that the distance here, the distance is going to be our dependent variable, so I'll put dv for distance, and then iv is time, so our independent variable. We just got to look at how they're changing as we move through time, okay? I think I did Alana, yeah, Alana is in orange. So how is Alana's distance changing as we move? Right, you may remember that, oh, Alana's distance is changing by 1. Right, but what's happening, actually let me use red here. And then you have to ask yourself, well, what's happening with our independent variable? You'll notice that simultaneously that the independent variable is changing by 1, and that's affecting our dependent variable to change by 1 as well. Okay. If we also take a look at Gilberto's, right? How is Gilberto's distance changing? Right, you might remember that we are adding 2 every single time. Adding 2, adding 2. So again, our dependent variable is increasing by a constant amount, and then our independent variable is also increasing by a constant amount. Okay? And then, you know, just we're going to oblige Leanne here, and we're going to say that their distance is increasing by 2.5 meters, I believe that's what we're in, every second. So to be able to tell from a table whether or not it's going to be a graph, well, some of the things that we talked about is that the independent variable increases by a constant amount, right? That amount is not changing, right? And then simultaneously, or at the same time, the dependent variable actually, I'm going to change the word increases to changes, because I'm sure you guys have assumed that increasing is not the only way to change an amount. So we can either increase or decrease here. So I'm going to change that so we can be as accurate as possible. Okay, and make sure you guys have constant amount in there. That's the important part. That constant is what tells us that this relationship is linear. Okay. Now, I want you guys to take a look at these equations here, right? So I'm going to circle them in red. So we have this d equals t, d equals 2t, and d equals 2.5t. What did you guys notice about these equations? Right? All of these equations represent, right? These equations represent this table. But how are these equations formatted? What do they look like? Right? Because these are technically linear equations, but we just need to describe what they look like. I really wish I was there today because I want to hear your guys' conversation about this. But I'm sure one of you have said that the independent variable is multiplied by it's multiplied by some number or some rate, right? You know, in our equations here, we have something like 2t or d equals 2t. We also have something like d equals 2.5t. So I'm sure if I were to write an equation like this, for example, y equals 13x, would you assume that that is linear or not? I would hope you guys would say yes, because you'll notice that it kind of looks similar to our d equals 2t and d equals 2.5t in the sense that our independent variable x, or t in this case, is being multiplied by some number or some rate, okay? So those are some ways that you guys can tell if a graph or if a table or equation are linear, okay? Now we're going to talk about, well, are any of these proportional relationships? And this was actually a question on your homework. Again, I wish I could have heard some ideas from you guys, because I didn't go over this with period 2, but period 6 we kind of talked about it. So we really need to go back to what the definition of a proportion is, okay? And remember that a proportion is just a set of equal or equivalent fractions. So a set of equal or equivalent fractions. Okay, so for example, we say 2/4 is the same as 1/2, right? If these two fractions, or we could even say if these two ratios are equivalent to each other, then we say that they are proportional, okay? So what we're going to do is we're going to write a ratio. Typically what I do is I normally do, I mean, it doesn't matter, but what you can do is the independent variable to the dependent variable, okay? So from this graph, what I'm going to do, I'm going to work in pink here. So from this graph, I am comparing the independent variable and dependent variable from Alana for right now, okay? So the ratio that I'm writing is the independent variable to the dependent variable, okay? And I want to make sure that these two pink boxes here are equivalent, right? And therefore makes them proportional. So what I'm going to write is my independent variable for the first row, right, is 1 second. Or sorry, not the first row, because the first row is all zeros. Okay, and I'm going to talk about that in a little bit. So we have 1, and I'm gonna write the unit so that way you guys kind of know where I'm getting these from. So 1 second, right? So from the seconds column. That's my independent variable. Then my dependent variable for Alana is 1 meter. Okay, so there's my first ratio, and I'm going to compare that to the next row down. So the independent variable in the third row here is 2 seconds compared to 2 meters. Now the question you need to ask yourself, are these ratios equivalent? Are they the same? Right? You'll simplify 1 over 1. You'll simplify 2 over 2 to 1 over 1, or in both of these cases, they are equal to 1. So we say, yes, those are equal. Let's double check one more. Let's double check the next two. So I'm going to do 3 seconds over 3 meters. Is that equal to 4 seconds over 4 meters? That's the question. As you can probably see, yes. So it looks like Alana's information here, or Alana's data here, signifies a proportional relationship because we can write these ratios and they end up being equivalent to each other. Okay, so let's test it for, I should have done Alana's in orange, but this is for Alana. Let's double check a few from Gilberto's here. So Gilberto, so again, I'm going to write the ratio independent variable to dependent variable. So I'll just write that to remind myself. And let's go ahead and write from the second row. Independent variable is 1 second. And then in Gilberto's data, the dependent variable is at 2 meters. And I need to double check that with 2 seconds. And he is now at 4 meters. Are these two fractions, are these two ratios equivalent? If you simplify 2/4, yes, you will get 1/2. Excellent. So it looks like Gilberto's is proportional. And let's just double check Leanne's for a good measure here. So Leanne, I'm going to compare the whole numbers when I write the ratios. So again, I'm doing independent variable over dependent variable. So my independent variable is, I'm going to use 2 seconds because my dependent variable is a whole number, and that's going to be 5 meters. Okay, and then I'm going to compare that to 4 seconds. And then the next whole number, which is 10 meters. Are these two ratios equivalent? Are these two fractions equal to each other? Yes, indeed. So it looks like all three of these relationships from Alana, Gilberto, and Leanne are proportional. Okay, so then, so we'll say yes, they all are. And now we need to answer this question. What is the constant of proportionality? Well, you guys might remember that the constant of proportionality is the same exact thing as the unit rate. And the unit rate in this case, hopefully you say it before I do, is the walking rate. So the constants of proportionality for each student, so for each student, is their walking rate. Okay, awesome. Okay, there's one other thing that I want to talk about for proportional relationships, and this will kind of apply a little bit more when we start looking at the graphs and determining whether or not the graphs are proportional. Okay, but I want you guys to notice the very first row of our table here. I'm going to highlight it. You'll notice that all of these lines pass through the origin, right? They pass through the point 0, 0. And this is going, like I said, this is going to be something we talk about a little later. But that's also a huge hint to determine whether or not something is proportional. So whether or not a graph passes through the origin, we can determine if it's proportional. We should write that down. Let's write that down. If a graph passes through the origin, and then in parentheses I'll put 0, 0, it might be proportional. And emphasis on might. Just because it passes through the origin doesn't necessarily mean that it is proportional. Okay. Let us continue. Whoops, I'll let you guys copy that for a second. Pause the video if you need to. Okay, let's keep going. So here's what we're going to do. I would like you guys to work on question B. So question B has 1, 2, 3, right? 3 questions built in. The one thing that I need to bring to your guys' attention is that it says for each student. So you guys must split the problems into Alana, Gilberto, and Leanne. Okay, so you guys can work together talk about the problems. You guys probably should only spend about, maybe about 5 minutes. We could extend it to maybe like 8 minutes if you guys really need it, but I don't think you need that much time. Okay, so go ahead, pause the video, talk to each other, and find some answers. All right, hopefully you paused the video and talked about this. Remember that we need to split this question into all three, or we need to answer the question for all three students. So for Alana, if time t changes by 1 second, by how much does the distance change? So you guys know that Alana's walking rate is 1 meter per second. So if time changes by 1 second, how much is Alana's distance going to change? Also by 1 second. So we'll write if time changes the distance changes by 1 second. Okay, so hopefully you guys did okay there. Whoops, I can spell. Okay, let's talk about Gilberto. What happens when you change time by 1 second? Well, if time changes by 1 second, and yes, I'm writing complete sentences, the distance changes by 2 seconds. Or 2 seconds. What am I talking about? By 1 meter, there we go, so there's Alana, and then 2 meters for Gilberto. Okay, and Leanne, I think, hopefully you guys are catching on to what's going on here. If the time changes by 1 second, the distance changes by 2.5 meters. Okay. Again, you guys, this is putting into words like your understanding and also just the relationship here is so important, because if you can explain it, then that means you understand it. You have a pretty good grasp on the concept. Okay. So the next question we need to answer is, how is this change represented in a table and in a graph? Right? So, I mean, we don't have to answer this for every student because they all kind of change similarly. So I guess over here in the left side is where I'm going to have to write. So in a table, right, you'll notice that as time increases, which is something we've already taken a look at, you guys. So as time increases, the distance increases by, whoops. Okay, close that. The distance, I only got 5%. The distance increases by the walking rate. Okay. Then I'll write in pink here. Well, what about in the graph? How do we see these relationships, right? If time changes by 1 second, the distance changes by 1 meter. How do we see that in the graph? Well, you'll notice that if you were to write out the coordinates for each point here, you'll notice that when the x-coordinate increases by 1, well, what happens to the y-coordinate? The y-coordinate increases by the walking rate. So the y-coordinate increases by the student's walking rate. Okay. So now we're going to do, well, never mind. You guys already should have answered this question, but you'll notice that your answers are kind of similar. Okay. So let's keep going. If t increases by 5 seconds, then how much does d change? So for Alana, if t increases by 5 seconds, d increases by 5 meters. So again, a similar pattern here, right? Let's see, Gilberto. If t increases by 5 seconds, d increases by not 5 meters, but by 10 meters. Okay, and then lastly we have Leanne. If t increases by 5 seconds, d increases by, what is 2.5 times 5? 12.5? Is that correct? Hopefully that's correct. Increases by 12.5 meters. Okay, and I'm not going to have you guys answer this part again because it's literally the same as what we wrote up here. So as time increases, the distance increases by the walking rate, right? So we can actually see that in a table, right? If we were to go up by 5 seconds rather than 1, you would see the change of 5 meters or 10 meters for Gilberto or 12.5 meters for Leanne, okay? And then the x-coordinate, well, if the x-coordinate increases by 1, then the y-coordinate increases by 5 meters, 10 meters, 12.5 meters respectively, okay? So let's talk about the walking rate per minute. Remember that the rates were given in meters per second. So Alana was 1 meter per 1 second. So we need to figure out, well, how many meters does she walk in 60 seconds? Well, you'll notice that you multiplied by 60, so you should probably multiply this by 60. So Alana walks 60 meters in 60 seconds. Gilberto walks 2 meters in 1 second. Then we're changing this to 60 seconds. And so we're multiplying this by 60. So you get 120 meters in 60 seconds. And then finally, Leanne walks 2.5 meters per 1 second. We want to figure out how many meters she walks in 60 seconds. Let's see, 60 times 2.5. I don't have a calculator on me, so I've got to do this by hand here. Whoops, what am I doing? That's 30. Okay. And then 2 times 0 is 0. 2 times 6 is 12. 0, 0. There we go. 150 meters per minute. So 60 meters per minute, 120 meters per minute, and then 150 meters per minute. Okay, and then we got to find the walking rate per hour as well. So if we take these new unit rates of meters per minute, so 60 meters per 1 minute, and we want to figure out, well, how fast do they walk per hour? So we're going to do 60 times 60 to get 3,600 meters per second. What am I talking about? Meters per hour, excuse me. Okay, and then we know that Gilberto walks 120 meters in 1 minute. So if we multiply that by 60, we'll get how many meters per hour. So let's do 120 times 60, 0, 0, 0, 0, 12, 6, 7. So it looks like 7,200. 7,200 meters per hour. And then lastly, we're going to take Leanne's right here and then change that to how many meters per hour. So 150 times 60, 0, 0, 0, 0, 30, 6, and 9. So it looks like 9,000. 9,000 meters per 1 hour. Okay. Last question in 1.2, you guys. For the friends who are part of the walkathon, made the following representations of their data. Could any of these relationships be linear relationships? Explain. So take a look, talk to each other, figure out which are linear, which are not. I will say that there are some that are linear and there are some that are not. So just be sure you can explain why they are or why they are not. Okay, so take about like 2 minutes, talk to each other, and we'll get back to it. All right, hopefully you guys talked about it. If we take a look at George's walking rate here, one way to check to see whether or not it's linear, remember the independent variable and the dependent variable have to change by constant values. So let's check the independent variable first. So you'll notice that it's increasing by 1 every single time. So good, we have a constant, it's increasing by a constant amount, the independent variable. Okay, let's check the dependent variable. So from 0 to 2 is plus 2, from 2 to 9 is plus 7, plus 9 to 11 is plus 2, plus 9, okay, so is the dependent variable increasing by a constant rate? I don't think so. Not quite. So we'll say George is not, and we'll write that it does not increase. Whoops, I can use grammar. Not increasing by a constant amount. Okay, so that's important. All right, let's check Elizabeth's. The independent variable, it looks like it's increasing by 2 every time. Yeah, so that looks good. And then the dependent variable, see, we're adding 3, we're adding 3, we're adding 3. Excellent. So yes, Elizabeth's walking rate. Good job, Elizabeth. You are linear. Okay. Now, let's take a look at Billy. Take a look at this equation here. Does that look familiar to you? Yes, it does. So we can assume that this is linear. We have the independent variable being multiplied. The IV is being multiplied by, we'll say a walking rate. The independent variable is being multiplied by a walking rate. So in this case, we do know that it is going to be increasing, the distance is going to be increasing, by 2.25 meters every second. Okay, so yes, cool. We got 2 linears here. Let's double check Bob's walking rate. Can we first review what do these variables stand for? T stands for time, and R stands for rate. Okay. Immediately what I'm thinking is, well, in the previous equation, in Billy's walking rate equation, we're taking the independent variable and it's being multiplied by a walking rate. But take a look at the rate here in Bob's walking rate. we're given a variable here. A variable is an unknown value. What's even more scary is that value can change, and therefore it is not constant. So because R is given to us as a variable, it's not given to us as a number, we have to assume that it could be really any number and it could change. So we will say that Bob's walking rate is not linear. Because R, and I'll say the rate here, because R can change, and it really shouldn't, especially if it's going to be linear. Okay, you guys. So that's it for lesson 1.2. I know that was a little long, but you know, I think we're making good sense out of this. Okay. Go ahead, take a minute, answer your focus questions, and then we'll dive right into the next lesson.